Okay, so couple things. First of all, the Lockheed Martin spokesman did not show up, so what we're going to have during his slot is a panel discussion with Jeff and Darlene so that more questions can be asked of both of them. And so if you'd come up here. But before, we'll just come up and do that, but just want to make sure everyone here knows that we have been videotaping or video recording every talk in the conference, and there are DVDs available on a table outside for sale. So, and very reasonable prices. So if you want to take the conference home, there's a way to do that. You should be sure to do that. I do want to make one comment on Jeff's talk, which was his last point is exactly right. Emphasis added. That is, the ISRU has the greatest benefit in allowing you to change the mission architecture to eliminate the second spacecraft altogether and eliminate the autonomous rendezvous and dock in Mars orbit, which is a major source of mission risk. And so, see, this is the point. When you have a technology and you trade it against another technology within a mission architecture that's designed for the other technology, you may only show marginal benefits. If, on the other hand, you say we're going to take each technology and we'll design the mission to be the best possible mission that it can be with that technology. In other words, you don't stick to the same architecture. You use the best architecture for Earth propellant, use the best architecture for in situ propellant, and you compare those two choices against each other, and that's where you find the true leverage in the system. And the thing about ISRU is it enables the direct return. And in fact, if you simply decrease your sample size a little bit, you now have a mission that can be landed with the Curiosity lander and go to the Martian surface and do a direct return from the surface, and we can turn the sample return mission from a vision into a mission. Okay. Anyway, that's my comment on that. But in any case, take the chairs, and we'll take questions for either of the two panelists. Sir?
This is a question for Darlene. The military is used to operating with unreliable or delayed communication. Is there any kind of operational experience that can be stolen from them?
Yeah, that's a great question. So let me just say this. So their systems nonetheless are optimized, or at least they try to optimize for real-time comms. And the delays, I think, are operationally, there are some nuances to them that are different than what we'll experience on Mars. So that's a long preamble to say, no, we have not actually had any sort of swip swap of information around what are their best practices in dealing with unreliable or intermittent communications. And so, or procedures where there's blackout, for example, which is fundamentally different. That's a great idea. And so a little kind of add-on to that is I found it difficult to try and find people who want to necessarily swip swap between, say, DoD projects and NASA projects. But the new thing that just got funded that I'm going to be working on over the next 4 years is actually doing a kind of best practices swap between the ocean sciences community and the community of people who are like myself who are interested in science operations in deep space and Mars. And so again, one of the things that, for example, the ocean sciences community does on Earth is they can't bring everybody with them when they do deep sea exploration. There's a ship, there's a finite amount of berths that are available. Sometimes there's only a dozen berths available to scientists, but there may be 50 people that want to get involved. So what they do is they have this incredible pipeline, this data pipeline, which is available to the broader community, where they'll be operating 6 kilometers down underwater with a robot, for example. They'll bring up the data, the telemetry, the video imaging, still imaging, whatever other spectral data they've got from underwater, up to the surface, and then broadcast that out across the world sometimes but to a whole bunch of people that are sitting remotely. And then their whole system, again, is optimized for real-time data aggregation, synthesizing, and then decision-making. But sometimes there are intermittent comms. So that's a pretty good analog for low-latency telerobotics. If you have, for example, a couple of people or 4 people orbiting around Mars, and they're operating a robot on the surface of Mars with low latency. So unlike what we currently do, where we have these communication delays between mission control and Mars with the exploration rovers or the MSL or whatever, if you have people that are co-located or closely located to those robotic assets, then you can reduce that latency, but you still have to have them at some point talk to Earth. So what we're going to be doing over the next 3 years is actually baselining the ocean sciences community's architecture in terms of how they deal with that kind of optimized, telerobotic system that they have. And then we're going to be experimenting within their architecture and putting in that delay. And we've got a science program, again, that is real. So again, you've got that science as a forcing function. And we're going to put in a 15-minute, maybe even more of a sliding scale kind of delay between the ship and shore, and then see how that whole system responds to it. So that's, and like when we got this funded, one of the things that was noted is, wow, that's really innovative to go out and try and learn from somebody else. And we were like, right on, I'm glad you saw that was valuable. But I think the military or military-funded programs, as well as maybe we can look to the aviation community more actively, and many other communities, search and rescue, that kind of thing, for how they communicate under these extreme conditions. I think is a great idea. So thanks for asking that question.
During both your presentations, I noticed a link. Hardware in the field. I'm wondering if there's a synergy there to remove some of those unknowns by maybe not flight hardware, but testing the scientifics in these in analog missions to help reduce that risk profile of new technology.
Yeah, absolutely. The more testing we do, the happier the engineers get that something isn't going to come up that they hadn't anticipated. In fact, one of the things I do, or I didn't do this summer, but have been doing for several summers, is my students do balloon experiments. So they send a balloon up to 100,000 feet, which is actually very similar to Mars conditions. It's very cold, very thin atmosphere, to sort of test technologies. And what we've been learning from these student balloon experiments is all of the possible ways to fail in Mars-like environments. And it's surprising how the students can come up with new and innovative ways to fail in the Mars Society. I'm always astounded at how innovative they are at coming up with new failure mechanisms.
I have a question. I'm a science fiction writer. I'm not a scientist, so this may sound stupid, but it's about 3D printing on Mars. And I heard something go by about producing steel on Mars and using it as feedstock. Did I hear that? Yeah. Dr. Zubrin is involved in that? That is real. You could do anything. I saw at a NIAC convention, I saw a 3D printer that was theoretically capable of constructing a habitat, presumably out of maybe sand, I don't know. But is it possible that eventually the return vehicle could be manufactured on Mars?
That's a bit speculative
Yeah.
for so far, but of course, for the science fiction purposes, absolutely. But I think for the early missions, we'd probably want to be well into the colonization period before we do that, and we probably want to launch a lot of unpersonneled launches before we want to put a person on a 3D printed launch vehicle. But for science fiction, go for it, absolutely.
Has anybody thought about sending a swarm of autonomous vehicles rather than covering the small track, that?
Yeah.
Okay. Has anybody thought about sending a swarm of autonomous vehicles so we could cover more ground rather than, the couple of feet that the one arm can reach off of something, be able to have them spread out and see a lot more?
Yeah, there's a lot of debate in the robotics community between the swarm robotics and the highly capable robotics. And about half of the robotics community is really excited by swarm robots. As far as I can tell, they are mostly excited because it's really hard, interesting challenges for the university people, and they don't want to just make something that's easy. They want something that's really hard. There's advantages and disadvantages to both approaches. In general, the bigger a rover is, the more capable it is of traversing terrain. So little rovers find little obstacles hard to traverse, whereas big rovers say, no big deal. It's a 10-centimeter rock, I'll just roll over it. So that's one point. Bigger rovers can carry more scientific equipment, and there's tons, literally tons of scientific equipment that the scientists want to take. On the other hand, as you point out, tiny robots, you could send swarms of them all over. They don't even have to talk to each other or interact with each other. And if one of them gets stuck or failed, no big deal. You have hundreds more. I was working in a project that actually we're going to do another proposal to do this, to send swarms of 20 to 50 rovers to a single site on Mars with the object of making a complete virtual reality map of that, so that anybody can go in and have a high fidelity virtual reality map, be able to walk around or play games on it or whatever. So we'll see if we can get some traction on that with the proposal. But there's something to be said for small, cheap, and large numbers. That's not necessarily a bad approach.
I'm going to add a little bit to it, if it's all right, because I find that question actually really interesting. And again, I'm just going to take us back to the ocean sciences community. So I think that one of the main things that we should probably do as a planetary science community or robotics community looking towards Mars is to try and scope the use cases for the different robotic systems very carefully, and then from there, systematically, do the very unsexy stuff, which is to come up with the requirements for each one. Because if you look at the ocean sciences community, again, they have a lot of area, surface area as well as depth to cover when they're trying to determine different or characterize different elements, associated with the ocean. So they'll use a swarm of, say, gliders, for example, or else a connected system of buoys. And then in other cases, they'll go and they'll do one-off, highly capable ROV, like working class ROVs that are the size of minivans will go down and do more directed, focused work. But again, that's, that each, hardware element or each capability is designed to meet a very specific requirement. So to me, there's less of a debate as to which one is better and more of a need for us right now to characterize exactly what it is we need when, and then to decide what is the best way to implement it.
I actually have to say, I think that NASA does rover programs exactly backwards. What we do is we say, well, we can land this much on Mars, go out to industry and say, well, how much is your bid for how much you will charge us to build a rover to go to Mars? But I think we should say, well, we can land so much on Mars. How much will you pay us to send your rover to Mars? And say, well, okay, we have enough room for 100 university robots. Which universities want to send their rovers?
Wouldn't it be very efficient to use hydrogen or helium balloons with mylar, photovoltaic mylar, releasing them one at a time? They would travel, wouldn't they be able to float in the Martian atmosphere, travel greater distances than your rovers would? And eventually, of course, losing their buoyancy, they would come down somewhere, and wherever they came down would be a new place to analyze. I mean, the balloons would be folded up to a very, very small volume, and when you release the hydrogen or helium, it'd be in a very small canister. It seems like you could have a dozen of these in a very small device.
Back in the 1990s, there was a lot of interest in Mars balloons when the Russians were going to fly a French balloon to Mars. There is a lot to be said for Mars balloons. They explore a totally different range of exploration than surface rovers. With that said, the Mars atmosphere is extraordinarily thin. Your lifting power is down from Earth lifting power by a factor of 100. So you need big balloons carrying lightweight payloads. So you can't carry very much. But as you say, you can get a lot of traverse capability. They would go long, long distances. We now have some orbiters that have some pretty good surface resolution. Back in the 1990s, when the Russians were talking about it, just the idea of getting this close-up view of, flying over Mars was a really cool idea. That's less important now because we have some pretty good views of the surface of Mars from Mars Reconnaissance Orbiter. But it's probably a sad thing that people stopped thinking about the balloons, mostly because you can only do so many things. You can't do everything. But yes, I'd love to see balloons on Mars. Here's the perfect experiment for balloons, by the way, would be to fly magnetometers. We know there's some very, very interesting things about the very near surface magnetic field on Mars. We've seen stripes in the cratered highlands in the southern hemisphere. Stripes are an indication of two things: an ancient global magnetic field and ancient plate tectonics. And both of those things are, oh my God, we need to know more about that. So a balloon mission with magnetometers would be very high on my list of things to do. Do you have more comments?
No, that's great. Yeah.
There is a German company that's still exploring balloons. I think they're called Artemis, but I'm not sure. And they're using hydrogen instead of helium because there's no oxygen to react, so it's not going to Hindenburg on you. Next question.
My question it kind of coordinates with the previous one about swarms of robots. Is there much discussion about scaling up the exploration of Mars and the collection of science from the planet? I mean, the window to Mars opens up only once every 2 years, and we send 1, 2, 3 robots at a time, and then we can analyze their data, for a couple of years. But it makes sense that we kind of know how to do this now, and we probably should scale it up so that we can have hundreds of robots that are highly capable robots all over the planet. Maybe the landers could serve as data centers. We have satellites to manage the bandwidth that's necessary to control and receive the data from all these rovers. We have like 1 or 2 or 3 basic designs, mass produce it so the cost comes down, and just try to send a whole entourage of landers to deploy this like in one mission, and then make a lot of universities happy.
Great idea. I nominate you for
yeah, me
NASA
too.
administrator. Let's do
Yeah,
it.
like,
Yes,
go,
yes.
you go.
Lots of exploration of
Yeah.
Mars. Perfect.
Yeah. Yeah, I mean, I think you'll get us going, yes, absolutely. There's just budget constraints, and will probably, but I couldn't agree more. It sounds like a great idea.
Spacesuits used on the moon, I assume, would be much too heavy in Martian gravity. What work has been done that you know to develop a spacesuit that can be used in Martian gravity in terms of mass and also having to last for months in terms of hours or days? And are there any analog training experiments in terms of how people would operate in a spacesuit with the weight that it would likely have on Mars?
Yeah, you missed the talk earlier in the session, but do you want to hit this one?
Yeah, sure. I didn't hear that talk either, but there are groups there's a lot of work being done at NASA Johnson, MIT, and there's one in I think it's North Dakota as well. I can't remember the PI's name there, unfortunately. But anyways, there are teams that are working on specifically that issue, and there have been analogs such as the NASA Desert Rats analog program that took place, I want to say in 2008 to 2010 or so, and that was out in Black Point Lava in Arizona. And what mass are you assuming? It was oh gosh, I don't know. I don't know the physics or any of the quantitative elements of it. You'd have to kind of look into what the groups are doing. It's not my area of specialty. But what I can tell you is that there are people that are working on it, certainly, and I'll tell you some of the things they've run up against. And so in terms of your question related to analogs and taking suits out into analog systems, for the people that I've been working with that are involved in EVA physiology, they've veered away from that over the past few years on land, not necessarily underwater and not in other sort of experimental lab-based systems that they have at Johnson, for example. The reason is because when we go out, for example, and do analog work in places such as Arizona, you're beholden to the gravity that we have on hand. And so you're wearing this suit. It doesn't matter what kind of, elements of flexibility or kind of, if you make the mass of the suit what it was on the moon or whatever you're going to do, you're still encumbered by what we have to deal with when you get out and walk around on Earth. So there is a real downgrade of the fidelity of the analog right away. So that's why they veered away from that. We get asked a lot when we go out into these analog environments, hey, are you going to wear a spacesuit? Because isn't it something important to do and it encumbers your vision and all that? And we just say no, straight up no, because there are so many other little details that we're trying to work out right now. And actually, what we found is that the engineers who are working on the spacesuits want us to do this without the spacesuits at this point. So we can tell them things like, when you go out and you're operating for 500 days on the surface of Mars, odds are you're not going to walk around like this the whole time. Odds are you're going to want to bend down. You're going to want to get your head under an outcrop. You're going to want to knock on things with very sharp instruments, maybe or maybe not. You're maybe going to want to have it actually have a system that's integrated into your suit itself that will allow you to interrogate the rocks, like a geological tricorder of some sort. Or maybe it's a biological tricorder. And so there are all these design elements that then will affect suit design, and you could umbrella statement things like you need to be flexible. No matter what the gravitational challenges are of whatever planetary destination you're going to explore, you need to be able to be a human being. And right now, the suits do not allow you to be a human being. You're a human in an engineered environment. So,
if you didn't see David Newman's talk, what was that, day before yesterday?
Yeah,
run to the DVDs and find her talk. It was not merely inspirational, but she also talked about her work on spacesuit, really far future spacesuit design and some of the criteria for it. It was a very good talk. Let me mention two criteria of lunar and Mars suits. The killer for lunar spacesuits was the lunar dust. Lunar dust turns out to be very jagged and abrasive. The statement from the people who examined the spacesuits after the Apollo, the longest Apollo had 3 spacewalks. That was at 3 times that they exited. And the statements of the engineers who looked at the spacesuits afterwards said that was good because they would not have survived a 4th spacewalk. The seals were too damaged from the lunar grit. The good thing about Mars is that the grit is not pointy and sticky. It is not abrasive. That dust I was talking about, the particles that we most worry about are micron scale particles. They're roughly the size of the particles in cigarette smoke. So you don't get the grit on the seals. It doesn't abrade the seals. On none of the rovers have we seen that failure. We've seen other failures. Lots of failures on the rovers. They are not working perfectly after 14 years on Mars. But grit was not one of them. I have to say, 20 years ago, we didn't know that. We had a lot of problems trying to design seals. So at least that one problem is not a problem on Mars. So good for Mars.
Okay. All right. This will be the last question for this session.
Okay. My understanding is that the 2020 rover would drop off the samples as it goes along, and then the Fetch rover would have to find each sample and pick it up and take it back. I'm wondering, that sounds a little crazy to me, and I'm wondering why they're doing it that way instead of just, why do you even need a Fetch rover, for instance? Why doesn't the 2020 rover just bring the samples back?
It's a question of mission architect. The scientists say we don't want a random sample of Mars. We get random samples sprayed off. We want particular samples. We want the rocks that we're interested. Geologist doesn't say, oh, bring me a rock from somewhere. I don't care what rock. The geologists say, I want this rock from this location. So the idea is, oh, okay, the capable rover can find the interesting rocks, do the core drills, and pick the rocks that the geologists want. As for why doesn't the 2020 rover just drive up to wherever the lander is, it's against the design lifetime of the rover. The question is that rover still going to be working? You land a highly capable vehicle to bring the samples home, and the rover says, oh, but my wheels don't work anymore. Can't you come to me? So the design that we worked in, and again, I said we didn't do the architecture. We did the engineering of the Mars Ascent Vehicle. The design given to us was that a really simple dumb rover lands with the Mars Ascent Vehicle, just enough to drive out, grab the sample, put it in, and load it in the rocket. So the rover on our vehicle was small and simple. It was not a Curiosity. It wasn't even a MER. It was little more than a Sojourner rover, enough to drive out, grab the sample, drive back.
Okay, thank you very much.
That was fun.
Yeah.